Hi students, today we are going to learn about an interesting phenomena that you must have seen in your daily life. We are going to learn about electric current. Electric current is all around you, isn't it? If you look at a bulb, the bulb is being lit by electric current. If you look at a tube light, again electric current, an air conditioner, electric current, hair dryer, electric current, fan, washing machine, fridge, everything involves electric current. So what is this electric current? There's even a law called Ohm's Law, which helps us understand electric current. We're going to study all about this in this chapter. And then some objects resist the flow of electric current. We are going to study about these resistors and resistor combinations in this chapter also. So let's proceed with this interesting chapter. Here we go. First of all, what is electric current? You see, in every conductor, there are some electrons called free electrons which are free to move throughout the surface of the conductor. What this means is they are not bound in the atom. They can move anywhere in the conductor volume. Understood? So these electrons, they move randomly here, there and everywhere. However, their net motion in any direction is zero. They just move randomly, so their random motion in all the directions cancels each other. Now, when you apply a potential difference across a conductor, however, these electrons start moving in a specific direction. So, for example, they move from the negative potential end to the positive potential end. This is what happens. So, in a way, you can even imagine that the electrons have become an electron gas. You see, in a gas, all the molecules move randomly. But if the gas is moving in a certain direction, then along with the random motion, all the molecules are also moving in a particular specific direction. Similarly, when a potential difference is applied across a conductor, the randomly moving electrons, they continue to move randomly. But the net cloud, the net mass or gas of electrons also moves in a certain direction from the negative potential end to the positive potential end. Now, the rate of net movement of charge through a conductor is what is called electric current. So the net charge flowing in a particular direction per second is called electric current. Understood? So as you can see, the number of electrons flowing from the negative potential to the positive potential in 1 second is electric current. So the net charge flowing per second is electric current. Interesting, isn't it? Now another interesting fact here is that the random velocity of electrons in general in metals is around 10 raised to 5 meters per second. This means that the electrons are moving here, there, in all directions at this speed. However, the velocity of the electron cloud, that is the velocity of the electrons in a specific direction when an electric potential or electric field is applied, is around 10 raised to minus 4 meters per second. So as you can see, the random velocity is much more than the velocity of the electron cloud, which results in the flow of electric current. Interesting again, isn't it? But I just told you so that you could keep things in perspective and see what is happening. So did you understand what electric current is? I can be written as dq by dt, the rate of flow of charge per unit time in a specific direction because of the electric potential applied or the electric field applied. Again, I can repeat it for you. The electrons are generally moving in random directions, but when a potential is applied, they move in a specific directions, and the rate of movement of this electron gas is electric current. One interesting fact that you must remember here is that the direction of electric current is always assumed to be opposite to the direction of motion of the electrons. So if the electrons are moving from right to left, the current is assumed to be moving from left to right. So basically we assume that positive charge is moving from left to right, when in reality electrons are moving from right to left. So mathematically, what is electric current? It is basically the number of coulombs of charge passing the cross-sectional area of the conductor in 1 second. So, if you imagine that this disc here contains 1 coulomb of charge, then the number of such discs passing per second through the area of the conductor is called electric current. The number of coulombs passing through the area is electric current. The unit of electric current is ampere. What is 1 ampere? It is 1 coulomb per second, because if there are n coulombs of charge passing through an area in 1 second, then the electric current is n amperes. Now, the electric current can be expressed in terms of the speed at which the electrons move in a specific direction. For example, these electrons here are drifting along in a specific direction because of the electric potential or electric field applied. The net speed at which these electrons drift, around 10 raised to minus 4 seconds, that speed, it is called drift velocity. So drift velocity is the net speed at which electrons drift in a specific direction when an electric field or potential is applied. Drift velocity is represented by the symbol Vd. Now we can express the electric current, the net charge flowing per second, in terms of this drift velocity. When we do that, we get this expression, I is nq A into Vd. Now of course, this expression sounds confusing. I mean, where did it come from? Well, let me tell you how this expression came. In this expression, n represents the net number of charge particles per unit volume. So you can say that this is, say, number of charge particles per unit volume. Q represents the charge on each charged particle. So it's the charge per particle. Understood? So NQ represents the net charge present per unit volume in the conductor, isn't it? Now we know that electric current is basically the amount of charge flowing per second. Therefore, it is equal to the net charge per unit volume into the volume of charge flowing per second, isn't it? That is obvious. After all, electric current is the net charge flowing per second. So that will be equal to the net charge per unit volume present throughout the conductor into the volume of charge flowing per second, isn't it? The volume of charge flowing per second is clearly the area of cross section of the conductor into the drift velocity, isn't it? The volume of charge flowing per second is area into velocity. There's no doubt about it. Therefore, the net electric current can be given by this expression that you see on your screen in this blue box. And yes, you must remember this expression. As you can see, N represents the number of charged particles per unit volume. Q represents the charge on each particle. So I is NQ A into Vd, where Vd is the drift velocity, A is the cross-sectional area of the conductor, and NQ is the net charge per unit volume in the conductor. This expression is very useful in solving objective type questions. Now, we know that the net charge flowing through the area of cross-section of the conductor per second is electric current, isn't it? Charge passing through an area in 1 second is current. The charge passing through 1 meter square of area in 1 second is given a special term called current density. So current density is the net charge flowing through 1 meter square of area of the conductor in 1 second. Current density is generally represented by the symbol J. As you can see, J is di by ds, current per unit area. Understood? So again, J is an important quantity that we generally use when we talk about electric current. What will be the value of J in terms of drift velocity? Clearly, J is NQ into Vd. After all, current was NQA into Vd, and J is the current per meter square, the current per area, isn't it? Therefore, J is NQ into Vd without the A. Now, there is something more that we need to learn about the current density. Sometimes you're given to calculate the current density and you're given an area S. In that case, you simply say that J is I by S, isn't it? Current per unit area. Now the problem comes when you see that the area across which you have to calculate current density is at an angle theta with the area perpendicular to the current. Understood? Area is not perpendicular to the current. It is at an angle theta as shown in this figure. In such a case, you cannot just say, that J is I by S if S is the area across which you have to calculate current density. In this case, you will have to take the component of the area in the direction perpendicular to the electric current. Understood? So for example, S here is like this, and the component of S in the direction perpendicular to the electric current is S cos theta, isn't it? So J will be I by S cos theta. It won't be I by S always. In fact, when we say J is I by S, we assume that cos theta is 0. When the area is perpendicular to the direction of electric current, then clearly theta is 0, isn't it? So this is again an important fact that you must remember, that J is I by S cos theta. When the area across which we have to calculate current density is an angle theta with respect to the perpendicular to the electric current, then J is I by S cos theta. Now sometimes a weird thing happens. We are given an area that is making different angles with the electric current, at different places. And we, are given the current density, and we are asked to calculate the electric current flowing through this area. This is a special type of problem asked in objective type questions. For example, let's say you are asked what is the amount of current flowing through this area, and you are given the current density J. Okay. Now, what will you do? You could have used the formula I equal to J into S, isn't it? You could have done this. But as you know, the area S that you use here must be perpendicular to the electric current. Now here, in this case, the angle made by the area keeps on varying with respect to the electric current, isn't it? It is some value here, some value here, and some value here. The area here makes an angle, let's say theta with this vertical. The area here is perpendicular to the electric current. The area here makes some other angle, say phi with the electric current, isn't it? So as you can see, how can you use the formula J equal to I by S cos theta? So if you are required to calculate the electric current through this area in this case, you cannot even say I equal to J into S cos theta, because even theta is varying. So in this case, you consider an elemental area here, and you calculate the elemental current flowing through this area, dI, and you say that dI, the elemental current, is J into ds cos theta. Understood? Because for this particular element, the angle theta with the vertical is constant, isn't it? So you can say, that dI is J ds cos theta for the elemental current. And then you can integrate this current from this position to this position, and you can integrate the right side like this, isn't it? And then you can express the value of ds in terms of theta. So di is J ds cos theta, and I is integral J ds cos theta. Understood? Now this is an important formula, and you must again remember it. This might seem a bit weird and confusing at first, but I can repeat what we have done for you. All that I did here was that I had to calculate the electric current when I was given the electric current density. So I said I could use the formula I equal to Js cos theta. But in this case, as you can see, theta keeps varying. The angle that the area vector keeps making with the vertical keeps varying. So I cannot say I is Js cos theta, because what is theta? So in this case, we take an element ds and we calculate the current through that element, di equal to J ds cos theta. The advantage is that for that particular element, theta is constant. Now we can integrate on both sides to get the final electric current passing through this entire semicircular area. A bit confusing, but if you ponder over it, you'll definitely get it. So those were the concepts related to electric current density, and the area across which electric current density is calculated. One more interesting fact that you must remember for objective type questions is that current is not a vector quantity, but current density is a vector quantity. Now current also has direction, isn't it? After all, when we say that current is flowing through a wire, the current is flowing in a certain direction. Still, we do not consider current to be a vector quantity. On the other hand, current density is always considered to be a vector quantity. We will not go into details of exactly why current is not a vector quantity or why current density is a vector quantity, as it is outside the scope of the IIT JEE syllabus. But for now, you definitely need to remember these facts. We can actually compare the flow of electric current to the flow of water from a tank kept at a higher level to a tank kept at a lower level. For example, current is equivalent to the mass flow rate of water in such a case. In the case of water, water molecules are flowing from a higher gravitational potential to a lower gravitational potential. In the case of electric current, electrons are flowing from one potential to the other potential. Similarly, the current density is equal to the mass flow rate of water per unit area. The drift velocity in the case of electric current is equivalent to the velocity of water as it flows from the tank at a higher height to a tank at a lower height, isn't it? So basically the flow of electric current is very similar to the flow of water. In the case of electric current, electrons are flowing, and in the case of water flow, water molecules are flowing, isn't it? In the case of electric current, it's the potential difference that causes the electrons to flow and the current to flow. In the case of water, it is the height difference which causes the water to flow or the water molecules to flow. Understood? If you visualize exactly how water is flowing, you will slowly start understanding electric current more. Now we've studied so many concepts related to current, current density, drift velocity, and so on. Let's now have a look at an IIT JEE problem to clear our concepts. Here we go. This problem was asked in IIT JEE 1997. A steady current flows in a metallic conductor of non-uniform cross-section. The quantity or quantities constant along the length of the conductor is or are current, electric field and drift speed only, current and drift speed, current only. Basically in this question, we are given a metallic conductor that has a non-uniform area of cross-section, and we are asked, across this metallic conductor, will the current vary, will the electric field vary, and will the drift speed vary? So we are given these three quantities, current, electric field and drift speed, and we are asked if they will vary. So let's take a look. So this is a metallic conductor. Now we know that current is equivalent to the mass flow rate in case of water flow, isn't it? So instead of imagining electrons flowing through this metallic conductor, let us try to imagine that it's water flowing through this metallic conductor, or water flowing through a pipe of non-uniform cross section. In that case, the mass flow rate, will it be constant or not? The mass flow rate will clearly be constant, isn't it? That's because mass coming in from one end per second will definitely have to come out from the other end in 1 second, isn't it? Because the net mass is constant, isn't it? Similarly, current is basically the charge flowing per second. So the net charge coming into this conductor per second must be the same as the net charge going out of the conductor per second. Therefore, current is definitely constant, irrespective of whether the area of cross section is constant or not. So I1 represents the electric current flowing out of the conductor on the left, and I2 represents the electric current coming into the conductor on the right. Now as you can see, I will be equal to NQA into VD, isn't it? We had just studied this formula some time back. Now at the left end of the conductor and at the right end of the conductor, N will be the same, isn't it? Because N represents the number of charged particles per unit volume, and that will clearly be the same, isn't it? In the case of water flow, the density is always constant, isn't it? The amount of mass per unit volume is always constant. Similarly, the amount of charge per unit volume will also be constant in this case. So NQ will basically be constant for I1 and I2. However, the areas of cross section at the left end and the right end will be different, because we are given in the question that our conductor has a non-uniform area distribution. Now we know that A is different for both cases, so the drift velocity must also be different, because as you can see, I1 is equal to I2. Therefore, A1 into VD1 will be equal to A2 into VD2. So when the area is more, drift velocity is less, and when the drift velocity is more, the area is less, isn't it? For example, here you can see that the area of cross section is more, so the drift velocity is less, and the drift velocity is more here because the area of cross section is less. Now since our conductor has a varying area of cross section, the drift velocity is definitely varying. So the drift velocity is varying and the current is constant. What about the third parameter given in the question called the electric field? Well, we already know that E is dV by dr, isn't it? Where V represents the potential difference across the ends of the conductor. Now if the potential difference applied across the ends of the conductor is constant, well, in that case E will become delta V by delta R, isn't it? And clearly it will then be constant if this is constant, and the length we are taking is definitely constant. In that case, the electric field will also be constant. But we do not really know whether the potential difference is constant or not. But if we assume that the potential difference is constant, then the electric field is also constant. Understood? So now let's finally take a look at our options. Let us see which of those options is now correct. Option A said current, electric field and drift speed are constant. This option is clearly wrong. That's because current is constant, electric field can be constant if the potential difference is constant, but the drift speed is definitely not constant. So this option is wrong. Second option says drift speed is constant, but we know that A1 V1 is A2 V2, so the drift speed varies as the area of cross section varies. Option number 3 is also wrong because again drift speed is not constant. Option number 4 is the correct option because it says only the electric current is constant, which is so true because we just saw that as in the case of water flow, when mass flow rate is constant, current, the charge flow rate, is also always constant irrespective of the area of cross section. So that was our final answer. So did you see, one IIT JEE problem tested all the concepts that we had studied up till now. Current, drift speed, and how current and drift speed vary as the area of cross section varies. Now that we have understood these concepts, let's move on to the next concept. The next thing we're going to study is Ohm's Law. It has been found that for most metals, the current density J is proportional to the electric field applied across the conductor. This is interesting, but scientists have found this fact. So if there is this conductor which has an electric field E applied across its ends, in that case the current per meter square flowing across this conductor will be proportional to the electric field. The proportionality constant is generally termed sigma, and so J is sigma E. Sigma is called the electric conductivity of the metal, and this expression J is sigma E is called Ohm's law. Of course, you must remember this expression as it is fundamental to our study of electric current. Sigma, the electrical conductivity, basically refers to how much current will flow through a conductor when a certain electric field is applied across the ends of the conductor. So the more the electrical conductivity, the more current will flow when electric field E is applied, isn't it? For example, if sigma is less, then you can keep applying a very large electric field, but the current density will still be less. But if sigma is very high, then even for a small value of electric field, a very large current density will be produced. This expression of Ohm's law can be further simplified to another expression, which is another form of Ohm's law. So as you can see, J equal to sigma E can be replaced by the expression J equal to E by rho. Rho here is 1 by sigma and it is termed as resistivity. So rho is a constant that is often used to replace sigma here. Now if J is E by rho, in that case we can say that I by A is 1 by rho into V by L, isn't it? J, the current density, is basically I by A, the current flowing per unit area of this green conductor, isn't it? The electric field, on the other hand, can be written as V by L. If L is the length of the conductor that we are taking into account, across which we are applying a potential difference V using a battery, then the electric field created inside the conductor will clearly be V divided by L, isn't it? Because E is dV by dr. This is equal to delta V by delta R if the potential difference across the conductor is constant. So when we make these replacements, and when we replace sigma, the conductivity, with 1 by rho, the resistivity, we get this expression. I by A is 1 by rho into V by L. On further simplification, we get V equal to rho L by A into I. The term rho L by A, where rho is the resistivity, L is the length of the conductor, across which we are applying the potential difference, and A is the area of cross section of the conductor. This term rho L by A is called resistance, and it is given a symbol capital R. So basically, rho L by A can be replaced by capital R, and therefore we can say that V equal to IR. V is the potential difference across the conductor, I is the current flowing across the conductor, and R is the net resistance offered by the conductor to current flow. This formula V equal to IR is the popular form of Ohm's law. This is the formula that we'll keep using again and again and again in our study of electric current. So this is another form of Ohm's law. The first form, of course, is J equal to sigma E, where sigma is the electrical conductivity. There is yet another term that is defined, and that is related to R, the resistance. Just as 1 by sigma is rho and 1 by rho is sigma, 1 by R is termed as conductance. So R is resistance, 1 by R is called conductance, sigma is electrical conductivity, and rho is electric resistivity. Now there are so many terms. There is sigma, there is R, there is rho, there is conductance 1 by R. So it's very easy to get confused between all these terms. So let us look at each of these terms and see what it represents physically. First, there is rho. Rho is the resistivity. It represents the resistance to the flow of electric current. This means that when a potential difference V is applied across a conductor, will the current flow, or will the flow of current be resisted by the conductor? So the amount of resistance that the conductor will offer to the flow of electric current, that is what resistivity approximately represents. R is resistance. Now R also represents the approximate resistance to the flow of electric current that a conductor offers. So if we apply a potential difference V across a conductor, will the current flow properly? How much current will flow? R decides all these things, because R decides how much resistance the conductor will offer. So what is the difference between rho and R? We already know that R is rho L by A. After all, we replaced rho L by A by R when we derived Ohm's law. So the main difference here is that rho is the property of a substance. It is independent of the length of the substance or the area of cross section of the substance. Rho is the property of any material. For example, iron has a certain value of rho. Glass has a certain value of rho. Gold has a certain value of rho. However, resistance is not independent of the physical properties of the substance. Resistance depends on the length of the conductor. It depends on the area of cross section of the conductor. So all bars of gold will have the same resistivity, but they will have a different resistance. If you take 1 meter of gold, which has an area of say 0.05 meters square, the area of cross section, and if you take 2 meters of gold, which say 0.025 meters square of cross sectional area, in that case both these bars of gold will have the same resistivity, because resistivity is a property of the material. However, both these bars of gold will have different resistance, because resistance also depends on the length of the material and the area of cross section across the material. Understood? A very similar difference occurs between sigma, the conductivity, and 1 by R, which is also represented by the symbol G, conductance. Conductivity is the property of the material. So again, iron has some conductivity, glass has some conductivity, and gold has some conductivity. However, conductance is different for the same substance depending on the length of the substance or the area of cross section of the substance. Understood? So that is the difference between conductivity and conductance. Both these parameters, however, represent how much current the substance will allow to pass when a potential difference is applied across it. So if a potential difference V is applied across a conductor, the more the conductivity and conductance, the more the current that will pass through the conductor. Understood? So the higher the value of conductivity and the higher the value of conductance, the more the electric current passing when we apply a potential difference V. So that is the difference between all these terms. Ponder over what I have said carefully and you'll definitely understand. I'll also tell you about the units of all these terms. Sigma, the conductivity, is measured in mho per meter. Mho, as you can see, is the reverse of ohm. Rho, the resistivity, is measured in ohm meters. G, the conductance, is measured in mho. And R, the resistance, is measured in ohms. The most common of all these terms that we will use again and again is the term resistance. But you must remember the units of all these terms. Just to get an idea of how resistivity values in general are like, and how conductors have resistivity values and insulators have resistivity values, we can look at the actual resistivity values of different substances at 20 degrees Celsius. Gold has resistivity of approximately 2.44 into 10 raised to minus 8 ohm meters at 20 degrees Celsius. Iron, however, is a lesser conductor of electricity compared to gold. So it has a higher resistivity value because it offers higher resistance to the flow of electric current. It has a resistivity of around 9.7 into 10 raised to minus 8 ohm meter. If you take glass offers immense resistance to the flow of electric current. In fact, have you ever seen, electric wires made of glass? Never, because glass is an insulator. So the resistivity of glass is 1014 ohm meters. A very, very bad conductor of electricity is water. Its resistivity value is 182,000 ohm meters. That is 1,82,000 ohm meters. Salt water, however, conducts electricity much better than ordinary water. This water that we are talking about is distilled water. So these were some resistivity values to give you an idea of how the resistivity values for conductors and insulators are like. And now that we've understood so much about all these concepts, let's move on to the next concept. Let's try to find out the temperature dependence of resistivity, because this is very important with respect to the IIT JEE syllabus.